Welcome to the final presentation of our senior design project for the Department of Electrical and Computer Engineering at Clemson University. In this technical design video, our team will be covering the technical details of our senior design project. We are Team 16, and for our project, we created a home monitoring system.
A home monitoring system is important for a homeowner because it allows them to see what is happening in their house in real time, whether they're upstairs in the bedroom or across the country. Owning a home is a big investment, so it is important to have a system in place to monitor for emergency situations such as break-ins, fires, or flooding. Of course, these events are rare, so the system should also be useful for day-to-day operation. Having a real-time monitoring system to display temperature, humidity, and light status can help the user keep track of their home's energy efficiency and identify ways to make their home more comfortable in the moment. We wanted our system to be relatively simple and cheap compared to other monitoring systems to market toward customers who don't necessarily need all the complex features of a more advanced security system.
For our design solution, we devised a home monitoring system with 7 modules sensing temperature, humidity, motion, sound, door opening, and water level. These sensors are connected to a Raspberry Pi microcomputer, which serves as a central hub for our monitoring system. The Raspberry Pi also hosts a web server developed with Flask. This server interfaces with the sensors, collects data, and hosts a web page that allows the user to view and interact with the monitoring system. From the dashboard, the user can view readings from each sensor, watch a live camera feed of their home, and arm their system to capture live images whenever motion is detected in the house.
This is the user interface for the home monitoring system. The status of each sensor can be seen in a card on this page. The following videos demonstrate how each sensor operates in the system. The temperature and humidity sensor provides the user with an ambient temperature and humidity reading in the desired location of the house. The temperature is measured with an onboard thermistor, which has a resistance proportional to the temperature. Similarly, the humidity is measured from the resistance of a substrate that absorbs water. The system then pulls the sensor every 2 seconds to receive the temperature and humidity readings and updates the web application accordingly. The flame sensor indicates the presence of infrared light detected in flames. It detects a range of 60 degrees over 5 feet. The wavelength of light detected is between 700 and 1000 nanometers, which is only present in light from flames or the sun. The sensor is connected to a digital pin that relays the status of the flame sensor to the web application. The light sensor indicates whether light of a manually defined intensity is detected in a given room or space. A photoresistor is used to detect whether light is present or not. An onboard potentiometer can be manually adjusted by the user to set the brightness threshold. A simple high or low signal is read by the Raspberry Pi to indicate whether the light is on or off. This allows the web server to be updated in real time when the light status changes. The motion sensor detects motion in its pointed direction. For this project, the motion sensor detects the presence of someone entering the front door of the model home. This sensor involves using a pyroelectric crystal to detect moving heat signatures. We had the sensor configured to send a signal to the Raspberry Pi when motion was detected. The signal would turn off after a certain amount of time until motion was detected again.
The door sensor indicates whether a door or window is open or closed. The sensor functions as a normally open switch with a voltage across it. When the door is closed, the switch is closed as well, sending this voltage to 0. The Raspberry Pi reads this voltage and determines whether the door is open or closed based on its value. The water sensor is able to indicate the amount of water it is submerged in. The sensor has a set of parallel exposed conductors, which act like a variable resistor whose resistance changes depending on the depth of water it's submerged in. The sound sensor detects any sounds that fall above a noise threshold. A microphone turns audio into a signal that is amplified by an op-amp on the chip. The amplified signal is then put through a potentiometer that has a user-defined resistance value. If the voltage across this potentiometer reaches a certain threshold, a signal is sent to the Raspberry Pi to indicate that sound was detected. The USB camera has two main functions. The first is to provide a live video feed on the web application, and the second is to capture an image when motion is detected while the system is set in armed mode.
A live video feed from the webcam can be accessed at any time through the dashboard. The system can be placed in armed mode. This mode will capture images from the webcam when the motion sensor is triggered. The captured images are saved with a timestamp and can be viewed by the user through the dashboard at any time.
While developing the system, we devised a set of criteria that, when met, would result in a satisfactory solution to our design problem. In general, we wanted each sensor to operate quickly and accurately, and our final system performed very well in relation to our parameters. Our sensors collected data and sent it to the web page in real time, satisfying our criteria for a fast and accurate monitoring system. The motion sensor immediately detected the presence of a human being within the desired range of 10 feet. The temperature sensor was tested through a comparative analysis to an external thermostat. The sensor produced accurate results within 2 degrees. The door sensor was tested to ensure that an accurate status update was produced within 1 second of an event. The flame sensor was tested to detect a flame within a 5-foot range after no more than 1 second of presence. The water level sensor was able to detect the presence of water at multiple different thresholds, with different readouts for 0 water, less than 1.5 inches of standing water, and greater than 1.5 inches of standing water. The light sensor was tested to ensure an accurate status update was produced within 1 second of a room light being toggled. The camera was tested to ensure it produced both a live video feed and captured images when armed mode was activated by the user. The sound sensor was tested to ensure an accurate status update was produced within 1 second of a noise being detected inside of the model home.
Our final system showcased a strong realization of our initial design concept. The base network of sensors that we developed functioned exactly as intended, and our modular design allows for modifications to create a more complex system with more sensors and app functionality. The system is also relatively inexpensive as a whole, coming in at just under $200. Some of the shortcomings of our project include a limited range of sensors and a lack of a native mobile application with push notifications. These weaknesses can be attributed in part to the limited scope and work duration of the project. Given only 4 months to develop our home monitoring system and limited group experience with mobile app development, our team decided to limit the scope of the project to ensure its completion. Our final web-based application provided all the functionality needed to showcase our home monitoring system using the programming skills our group members have developed during our time as electrical and computer engineering students.
This project was developed by Tim Driscoll, Zachary Jordan, Jackson Murrin, Austin Rep, and Dylan Sham. We would like to thank you for watching our video.